Today we're going to take another look at limits, how we think about limits, our intuition of limits, and how that intuition has to get translated into this kind of messed up definition, this weird definition to make stuff work. Then we're going to look at, we looked at a few examples in a graph yesterday. Then we're going to see where we can use this limit business in a concept called continuity. All right. So the intuitive words that we use to describe limits is we say that f of x approaches L as x approaches C. The definition is set up where we say the limit as x approaches C of f of x equals L if and only if for every epsilon greater than 0, there is a delta greater than 0, such that the absolute value of x minus C less than delta implies the absolute value of f of x minus L is less than epsilon. That's like our statement of what the definition of a limit. A statement of what we mean by this phrase right here. If we cannot find such a delta for any given epsilon, then that we say this limit does not exist. The intuitive idea is that as x is getting closer to C, f of x is getting closer to L. That's a little too hand-wavy. So the way we set it up, like I was there, the way we set it up is to say we can make f of x as close as we want to our proposed limit L, so long as we make x sufficiently close to C. We can make f, everybody likes that one. I'm a narcissist, so when I hear applause, I assume it's for me. I'm just kidding. I just like to point it out because in some other classroom, in this classroom, it's like all math. In some other classroom, there's applause. Oh man, what's going on? And then they're going to be like laughing and stuff like that. That class sounds way better than this one. And you're going to find people from that class like, oh, what is your major? I want the fun class. Okay. This is a fun class. Fun, goddammit. That's 2 Bull Durham references in a row. All right, so the idea is, oh, question? Uh-huh. That's what we're talking about a little bit today. So what the idea is that we can make f of x as close as we want to L. That's what this part of the statement says. So long as we can find this delta so that when x is this close to C, x is within delta units of C, that guarantees this statement over here. So I want epsilon to be within 1/100th of L. Oh, sorry, I want epsilon to be 1/100th. I want f of x to be within 1/100th of L. What delta do I need to make that happen? So if, for example, oops, I spelled limit wrong. So yesterday we looked at this example. In this example, we actually use the fact that we can simplify this. This is almost continuous. X squared minus 4 over x minus 2. The only place that's a problem is the 2, and we can cancel out that problem factor from the denominator and essentially plug in the 2. If I get rid of the x minus 2, then it seems okay to plug in the 2. Then 2 plus 2 get 4. The limit is equal to 4. I can make this function, x squared minus 4 over x minus 2, as close as I want to 4, so long as I make x close enough to 2. So When I see x squared minus 4 over x minus 2, we're secretly thinking of x plus 2. The superhero pedantic man is in the corners like, oh, so long as you're not thinking of x equals 2, right? And we're like, oh, yeah, whatever. Pedantic. That's everybody's reaction to pedantic man. I can make x squared minus 4 over x minus 2 as close as I want to 4, so long as x is sufficiently close to 2. So we know what the graph of x squared minus 4 over x minus 2 looks like. We've got a line with a slope of 1. I have a grid on here, and I can barely see it because old. So there's a hole in the graph when x is 2. There's a hole in the graph when x is 2. That there should be a point when where the function is equal to 4. That's where the function was headed as we're approaching 2. But as soon as we get to 2, nothing. There's a hole in the graph. We can make f of x sufficiently close to 4. So if I want I didn't draw enough underneath. So what we want is we want to guarantee, what do we have to, how close does x have to be to 2 to guarantee that y is within epsilon units of 4. So plus epsilon minus epsilon, where epsilon is as close as we want. I want f of x to fall inside of this range. How close does x have to be to 2 to make this happen? So we're looking, if we decide on, we decide how close we want f of x to be to 4. And then we go look how close do we have to make x to 2 to make sure that that happens. So we start by choosing a value for epsilon. Let's say epsilon is 0.1. That is, I want between 3.9 and this function. I want this function to be between 3.9 and 4.1. I want this to happen. What value of delta do I need to make this happen? Thank you. Well, we can see that we have this, this x squared minus 4 over x plus 2. We're thinking of this as x plus 2. We're thinking of that function as being just x plus 2. Pedantic man's like, oh, hey, stay away from that too. And then I go, got it. In my mind, pedantic man looks like Homelander from The Boys. So that's what you need to picture if you want to picture the same thing I'm picturing. So then if we add 2, I made this exceptionally easy on us to say that x needs to be within, let's see, subtract 2, 2.1 and 1.9. So if x is within 0.1 units of 2, then we're guaranteed our function to be within 0.1 units of 4. If x is within 0.1 units of 2, then f of x will be within 0.1 units of 4. This is just an example with some numbers. I gave myself a function with a slope of 1 because lazy. We have to be able to do this for any choice of epsilon. That's the as close as we want. Then we have to be able to find this delta. That's sufficiently close. With the piecewise defined function we had yesterday, if I pick one of these endpoints to be L, like this top one, if I try this as L, up on top, we'll have L plus epsilon. And down at the bottom, we'll have L minus epsilon. This works on one side, but it doesn't work on the other. If I pick any kind of delta, but then subtract see how this delta works on the right side of our graph, but on the left side of the graph, if I go C minus delta, the function is not in this range. The function is not within epsilon units of L. And this is the situation no matter what L I try to put as a limit for this function. No matter what we try to choose for the limit of this function, I'm not going to be able to get the function inside that range. If we choose epsilon to be big enough, that's not the question. The definition says for every epsilon greater than 0. It's not okay that it works for this one, for a particular value of epsilon. It has to work for all of them. We can't use anecdotal evidence. This works. My cousin did it. Does that work for everybody? No. And then it doesn't work. Any questions? So that's what we mean by sufficiently close. We can find a delta so that the function is as close as we want to the limit. How's everybody okay? All we have to do now is say that so many times you can't not say it. I'm trying to get a song stuck in your head. I can't just say it once. I have to say it over and over again until you're sick of hearing it, until you can't get it out of your head. How's everybody okay? Everybody looks so very sad. Well, this seems very repetitive. It only seems very repetitive because it's very repetitive. That's how things get stuck in your head. You get better at this by doing thousands of problems. That's the way to get better at it. You do thousands and thousands of problems. It's funny, a lot of times in math class, we don't give ourselves a chance. This is a thing that happens. We don't give ourselves a chance in math class. Y'all come into a math class, and I go, we're going to do a new thing today. Here, let me demonstrate this new thing. And then we do like 1 or 2, maybe 5 examples. Great. You have watched someone do 5 examples. And then you go home and you're like, oh, why can't I do this? Because you watched someone do 5 examples. You have personally done 0 examples. Even if you've done 1 or 2 examples, because the teacher was like, oh, here's 5 examples. Now you try one. And you're like, oh, okay, I've got it. I've done this once. I've got it. You don't get to start thinking that you're going to be good at it. That's not how anything works. Except that one friend that's good at everything. But fuck that guy. You might have to do some more problems. Here's the thing. So let's say you come to class, you watch me do some examples, and you go home and say, oh, why can't I get this? I've watched a lot of baseball. You know what I can't do? Hit any kind of pitch whatsoever. But I've watched so much baseball in my life. How come I can't do that? Because I haven't done it. I'm going out and practiced, hitting thousands and thousands and thousands of pitches. So it makes sense that I'm not good at hitting baseballs. Same thing happens in math class. You can't just watch somebody do like 5 examples and then think you're gonna be able to do it until you go home and miss a bunch of times. Does that make sense? The big difference, I have physical limitations on hitting baseballs. When something's coming this way, if I'm looking at it even a little bit at an angle, my eyes are like, oh, nah, fuck this. I can't keep track of that. And like the ball disappears about 20 feet away. It's like, oh, where'd it go? And the catcher's like, oh, it's right over here. I'm like, oh, fuck. So I just got to swing and hope the pitcher can hit my bat. That's my strategy of hitting. It doesn't really work out very much. The good news is there's nothing that's going to physically stop you from learning math. All that math wants from you is time. That's it. It's a variable amount of time. Some of you, math is going to demand more time from some of you than some others. Some people are going to watch me do 5 problems and all of a sudden magically get it. Now, who fucking cares? Good for them. Eventually they'll find the class that becomes the wall. They'll hit a wall sometime. Maybe they won't. Maybe they'll be the next famous mathematician. But that doesn't affect you at all. You just need more time then. All that math wants is time. There's nothing physically stopping you from learning math. There is nothing that will physically bar you from understanding math. The only thing you need is time. I guess that's a physical limitation. Eventually, we're all going to die, so you're out of time at that point. So far as we know. Questions? You just have to decide that you're going to. That's the most important part. Decide that you're going to, and accept the fact that it's frustrating and annoying. Here's the messed up page. Which is also messed up. Limits are a tool, a way of describing something kind of rigorously. Well, we're headed there. That's where we're headed. That's where we're headed. Let's talk about one of the places limits show up. One of the places that we need to have limits is continuity. Continuity is an old concept, but it wasn't rigorous when we first started thinking about this concept. Our original concept of continuity is like, okay, you could draw it without having to lift your pen up off the paper. That's like your intuitive idea. A function is continuous if we can draw it. No gaps in the function. This one works pretty well. No gaps in the graph. So what we might say something like the function x squared minus 4 over x minus 2 is discontinuous at x equals 2. So this says a lot about this concept of continuity. Discontinuity happens at a point. If we try to draw the graph of x squared minus 4 over x minus 2, there is a gap in the graph when x is equal to 2. The graph, we draw up, we have to stop before we get to 2, then we pick up right after 2, as if there's a thing called right after 2, and then keep going. We have to jump over the 2. Drawing the circle doesn't count. You can't be like, oh, I'll just go around, I'll just keep my pen on the paper to draw the circle. Nah. That's not what we mean, and you fucking know it, so knock it off. Unless you're playing in a D&D game, then absolutely knock that shit back on. And I go, you didn't say this. It's like every D&D player, it like brings out the Fey contract lawyer in you. It's like, what did they say exactly? No. So you know what I mean. So this represents a hole in the graph. I'm just trying to make it visible because that hole is exactly one real number wide. So it's an infinitely small hole. There's no way we're going to be able to see it, especially with a pen that's this thick. So there's a gap in the graph. Even if I try to define that function with a piecewise function, I might say something like f of x is this piecewise defined function. It's going to be x squared minus 4 over x minus 2. This is if x is not 2. But it's just going to equal 5 when x is equal to 2. Aha, now the function is defined, right? F of 2 is equal to 5. What's the problem with this function? What happens? In our first function, in our first one, f of 2 was just undefined. There's nothing there. Undefined. Here, in this function, I should call it something else. G of 2 or something. Sorry, g of x. G of x is different. G of 2 is defined. What's g of 2 equal to? 5. Does that help us make a continuous function? No, what happens? All the way up to 2, 5. Back out. No. We had to take our pen up, draw that point there, and then come back down and then continue. There's still a gap. I didn't fill the hole in the graph. I didn't fill the gap in the graph. So here we have just undefined, a gap. Here, the function is defined, but kind of in the wrong spot. What should I put here to make a continuous function? 4. Where did you get that number from? We got that number from the limit. So now when we draw h of x, There's the graph everywhere but 2. But now our function is continuous. We have plugged the gap that was there. F of x is discontinuous at x equals 2 because it was just undefined. G of x was discontinuous at x equals 2 because it was defined in the wrong place. The value, the depth, where the function is defined was not the same as the value of the limit as x approaches 2. H of x, the function is defined and the value of the function is the same as that of the limit as x approaches 2. This is how we define continuity at a point. The limit is equal to the value of the function at the point. So we say a function f of x is continuous if and only if I should list 3 things here explicitly. I explicitly state one thing and kind of imply the other 2. The 2 things that I'm implying when I write this statement is that this limit exists and that this value is defined. So the 3 things we would have to say, a function f of x is continuous, at x equals c. This is continuity at a point. A function is continuous at x equals c if and only if, 1, the function is defined at c, 2, the limit as x approaches c of f of x exists, and 3, those values are the same. The limit exists, the function is defined, and those values match up. The limit exists, the function is defined, and those values match up. Here, the limit exists, the function is defined, but the values don't match up. Here, the function is not defined. The limit exists, but it doesn't matter because the function is not defined. So the extra other things that are implied here f of c is defined. And it's also implied that the limit exists. If we're saying that a function is discontinuous, there's going to be one of 3 things. The function is not defined, the limit does not exist, or those 2 values don't match up. Any questions? This is what's required so that when we're drawing the function, we don't have to lift our pen off the paper to draw the function. Yes. No. We can add each of those 3 things. They can be separately true or not true. So like for this first example, f, the function is not defined, so not continuous. In g of x, the function is defined, but the function is defined and the limit exists, but those 2 values aren't the same. That's why it's discontinuous. So those, the three things, function is defined, limit exists, and values are the same. Those three things can all are all separate things that we have to check. If it's true at C, then if all three of these things are true at C, then we say the function is continuous at C. We only get C. Everywhere else, we don't have the problem. Here, the only place that in F, the only place that the function is undefined is at 2. It's continuous everywhere else. But we didn't get that based on this. That's just clear because the function is defined and we can just plug in values. There's nothing weird going on. Questions? Intuition, no gaps. You can draw it without lifting your pen off the paper. Here's what it means with our limit definition. How's everybody, okay? You should be amazed at all the stuff that you get to know. Like just like a couple hundred years ago, no one knew this kind of stuff. You're gonna finish all this calculus and you'll probably be like within the top 10% of people around the world as far as mathematical knowledge goes. This is not something that just everybody knows. And I think I'm being fairly generous when I say like 10% of the world's population knows calculus by the time they're in their early 20s. I mean, just think back to like the Pythagorean theorem. Someone tell me what the Pythagorean theorem is, how we remember it in the modern age. How would you state the Pythagorean theorem in the modern age? A squared plus B squared equals C squared. Do you think Pythagoras ever said A squared plus B squared equals C squared? You could tell by the way I'm stating the question, no. And why is that? Yeah, but the main reason you wouldn't say A squared plus B squared equals C squared is that's using algebra, and poor fucker didn't have algebra. We have algebra. We teach algebra to children, of all things. And that guy didn't even know it. He never heard of it. Also, boss move, naming the Pythagorean theorem after yourself, because that was an old result when he got his hands on it. He's like, well, the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. And students are like, oh, holy shit, did you come up with that? And he's like, well, you've never heard of that before? And his students are like, oh, nah, man, we never heard of that before. He's like, well, yeah, I named that. I came up with that. That's my idea. That's why I named it after myself. That's the Pythagorean theorem named after me, Joe Pythagoras. Yeah. And they're like, oh, hey, our teacher thought of this whole thing. And then like other mathematicians from around the world are like, oh, motherfucker, we've been using that for hundreds of years, maybe even thousands. It's like, well, we named it for him. And Thomas Edison was like, oh, yes, this is how I will live my life. Steal it all. All right, that's it for today. I'll see you all on tomorrow. Everybody think about continuity. Have a good day, and thanks for playing.